address and then manipulate that numerical address to arithmetic, and that had very profound consequences. That's there's Gödel and Einstein. When Neumann, on the other hand, went completely in the other direction, he could see the war was coming, so he decided to study explosives because he, of course, hated the Germans and even ahead of everybody else, he hated the Russians. And used that knowledge to develop the implosion system by which we were actually successfully able to do weapons. There was the Institute for Advanced Study just doing this very abstract stuff, and then there was Los Alamos making it all real with hardware and machine shops and high explosives. And it worked. So in an incomprehensibly short time, in 2 or 3 years, the time it takes us now to sort of develop a business plan, they did the physics and built and exploded it and used it in the war. Whether it won, whether it affected the war is another question. So the people who would come into the war, like Von Neumann, Richard Feynman, and Stan Ulam, as completely abstract theoretical physicists, they came out of the war having been allowed to work with high explosives, machine tools, and they were not going back. They were not going back to this abstract theoretical war. They wanted to do something. And what was it? It was going to be computers. That was the next big thing after the bomb. And that's how they got the support, because the government, the people with the money, were like, if you guys did the atomic bomb, sure, we'll give you the money to do computers. And we had, of course, they were doing both bombs and computers. So there's Johnny von Neumann with Werner von Braun, the other bomb. Von Braun came from Germany and really established the American space program. And all the rockets we used to use were still really a product of von Braun's program. And at that time, not only the British had this computer I showed you a picture of, the Colossus with the paper tape, we had something called the ENIAC. And the British kept their computers secret. They were sort of embarrassed by the fact that they really won the war by sneakily, by stealing codes. Yet, we publicized the ENIAC. So that's really how the Americans took over the world of computing. That's Herman Goldstein, who then went from the ENIAC to work for von Neumann. That's the operator's maintenance manual for the ENIAC, which even the maintenance manual was a restricted document. So until 1946, computing was still classified. The other person in this puzzle is the fellow in the middle of life. That's Zworykin, who escaped from Russia, and he brought the Americans television, which was actually a Russian invention. And then he wanted to go into computing. And the way he wanted to do it was with this thing called a selectron, which was essentially what we now would call an integrated circuit within a vacuum tube. This was a 4,096-bit random access memory within one vacuum tube. It completely was the missing link between the world of analog vacuum tubes and the world of digital computation. And it's a very important part of why we are here today, because the architecture was designed for this tube. Even though that tube didn't materialize, that's how we were so ready for the silicon chips when they came. So the first meeting of von Neumann's project was in Zworykin's office in November 1945. And then they deliver, at this meeting number 1, they deliver sort of the 3 commandments of digital computing. There's a central clock. So this is what gave us the clock cycle. We do everything, at that time they were like 16 kilocycles. Now we're into the billions of cycles. The design is modular, so when something goes wrong, you can pull out that motherboard, you can pull out that memory chip and just plug it in. And most of this is the ultimate commandment of computing. The words coding the orders are handled in the memory just like the numbers. And that was, up till that time in the history of civilization, there were 2 kinds of numbers that were used to represent things. You had 6 oranges or 6 apples. Now, we have numbers that are allowed to do things. They become order codes, and they give the instructions to the computer. And that's what sort of changed the world when we had numbers that could actually affect real things in the real world. That's sort of how numbers took over our universe, and we live in that world now. This is a piece of paper. When I'm doing all this research, I found all these people who had been involved in this and got in their basements. And Julian Bigelow's basement. These are all New Jersey basements, which is like the worst possible place to keep paper. So this is a piece of paper that had been crumpled up and uncrumpled. It says, let a word 40 binary digits, so they hadn't invented the word bit yet, so this puts it into late 1945. The two orders, each order equals command and an address, and so that, as far as I can tell, is the origin of the command line, the way all, many, many levels below what's running on my Mac here, there's still a command line giving the command and the address at which that command takes effect. Then the question was, so this was after the war, there was no housing in Princeton, the Institute was full, the League of Nations from Geneva was in the upper floor. So where can they put this group if anyone wants to bring it? It was agreed that the room connected with Dr. Gödel's office might be used for people working on a computing machine. Because Gödel was enough of a professor to have an office for a secretary, but he didn't want a secretary. Gödel wrote something down about once every 2 years. So that was the only empty room in the entire institute, and that's where they put the original computing group who wrote these first reports. It established the architecture of all our computers in use today. And in many ways, these were Gödel's ideas about how you address, because Gödel's great work, he had shown how you could encode mathematical statements in a different language, in an arithmetic language, and I think von Neumann clearly took some of that. The secretary, Akrivil, who was Greek, she was hired when she was 16 to work on ENIAC, and then came to work for von Neumann when she was 7. She's going to be the last person still alive. She's still alive and well in Los Angeles. And she typed all those early reports on a Verityper that has a disk, so you can change the typeface. She finally got her own computer in 2009. This is their budget. So the budget from November to April, the first 4 months, is $4,705. So you can change the world with a very small amount of money. Then in May, sort of the beginning of the end happens. The Institute had a crew of theoreticians and historians who absolutely objected to engineers and laboratories and so on. So now in May, we have the first $4 for electrical work. And that was the beginning of the end. And then things had to be decided. So something we take completely for granted. This is an and/or gate. Like now, like and/or gate is something that's in the, it's in the fabric of the universe. You don't have to invent it. But at that time, somebody had to invent the and/or gate. And all this was done with vacuum tubes that are not digital and binary. And so there's a very faint region in the middle that actually acted in a binary way. And how do you connect all these cells of communicating vacuum tubes? All done on sort of a blank slate. And it's very important to go back to that period and look at what people were thinking at the time. This is the shift register. Again, just taken as absolutely for granted that your computer will have a shift register. This is shift register number 7. And what about number 6, number 5, number 4? There were many different variants looked at until they settled on the one that became the one we all use today. And that's prototype of shift register number 7, the one that was adopted. So all the bits go up and are interlocked before they come down. Now that's why this machine can run for a billion cycles a second for 3 weeks without ever losing a bit. It all has to be wired by hand by these engineers who were not welcome. And a lot of the work, the repetitive work, is actually done by high school students who Julian, that's the engineering group. The whole crew there, you don't see them all. And now, the problem, where are we going to put these? Now there's 15 people. This is the director writing to them. The only really usable space in our basement is that adjoining the men's laboratory, to which you are most heartily welcome. That's where they ended up. And if you go look for that room now, it's now the main server room of the Institute. It has like a 50 megabit per second digital switch to the outside world and fiber optic lines. Now, this is one of the classical scholars objecting. I've learned some dismayed group of electronic experts has moved into our half of the basement. Mathematicians in our wing over my dead body. It's interesting, immediately divided between them. The idea was to bring historians and mathematicians together. They hated each other from the beginning. So that's the engineers. And now the director is writing to them. I'm having a little trouble about the T-service The members of your staff consume several times as much supplies as the same number of people do in Fall Hall. They've been especially unfair in the matter of sugar. Sugar is still being rationed. Even though the war is over, but actually things were more in short supply after the war. So they say they should come up with a proper supervision to get their teeth. Meanwhile, they're doing all this great work in producing these architecture we follow today. The machine, it was a work of genius. It was built by Julian Bigelow, who was an engineer. He built it. To him, it was a V40 engine with 40 cylinders, and that's what it did. It cycled numbers, and it was just absolutely beautifully engineered, built like a work of art. And all our microprocessors, every single chip that you've got 30 of them in your iPhone and 50 of them in your car, they all are exact copies of this architecture still today. Just got like the original sort of language of DNA, got cast in stone. And the reason that happened was because that Selectron tube RCA never got this Selectron finished in time. So these guys were desperate trying to figure something out. So they used off-the-shelf oscilloscope tubes. These were Wurster plus 5-inch you could buy for $30 or $40 each. And incredibly clever way. They took this analog device and they put an amplifier on the face, and that's how so in 0.7